Hello, my name is Yossi Ben David. I'm from Israel, and I'm going to discuss about my joint work with Avi Segal and Kobi Gal, sequencing educational content in classroom using Bayesian knowledge tracing. So there is a lot of research about mastery learning, and there is also a lot of research regarding sequencing. But there is a gap between those two topics, and we wanted to bridge that gap with our paper. So our main research goals was that we came up with a mastery learning model that fits the data of a real classroom environment. And we use that model to sequence educational content to students in a way that best fit their learning needs. And then we evaluate our algorithm in a field study, in a real classroom environment. So this is a more illustrative way of our approach. So we use the data set of LNet company, which contains millions of records of students that work in e-learning systems, with more than tens of thousands of students who use that system. I also want to say that I work at LNet company in the last 5 years, and I feel that I'm very fortunate that I got the chance to do my research with the company that I work at. And they were really helpful with that research. So we used that data from the LNet company. We cleaned the data. We did some feature selection. And then we came up with a mastery learning model. We used that model to sequence questions to students. And then we evaluate our sequencing algorithm in a classroom testing. So the most common way to do mastery learning is Bayesian knowledge tracing. I'm sure that probably all of you know it, but I'm going to just say a few words about it, or maybe to remind some of you who doesn't know about it. So the idea behind the Bayesian knowledge tracing is that it's a hidden Markov model with two states, either a student in a not learned state or in a learned state, and with 4 latent variables. The probability of guess, which is the probability that if a student in a learned state, if a student in a not learned state, what is the chance that he will get a question correct, will guess it right. The probability of slip, that if a student in a learned state, what is the chance that he will slip and get a question incorrect, or 1 minus probability of slip and get a question correct. The probability of transition to move from a not learned state to a learned state, and the probability of L0, which is the prior knowledge in that skill. A skill is the most basic unit that a student needs in order to solve a question. So when we took that BKT to a real classroom environment, we faced a few challenges. One of the challenges that we faced, since we wanted to come up with a sequencing algorithm, we needed to take the question difficulty into account. We also saw that students solve the same question multiple times, and we believe that student who solve a question for the first attempt is not the same as student who solve the same question in his third or fourth attempt. So we believe that there is knowledge in the attempts of the students. We also saw that in many e-learning systems, there is a partial credit score method to score the student's grade. So we wanted to take that into account. One of the assumptions of BKT is that the student can get a correct or incorrect response. And lastly, we saw that students from different ages solve the same questions. So we wanted to capture that knowledge too. So luckily for us, there are some work that was done about some of those challenges. In order to take question difficulty into account, Pardos and Effernan came with a new model called the KTIDM, the Knowledge Tracing Item Difficulty Effect Model. And the idea behind that is that they introduced an item node to the BKT topology, and they learned the probability of guess and the probability for slip for each item node. I also want to say that I was really inspired by their work, and I felt that one of the main reasons for me to go to that research direction was because of that work. So I just want to put it out there. So to face the multiple attempts on questions, Pardos et al. Came up with a count model he needed to face that challenge when he adapted the Bayesian knowledge tracing to MOOC environments, and he also had multiple attempts for each question of the students. So we also faced that challenge, and the idea behind the count model is that they introduced a count node and they learned the probability of guess and the probability of slip for each attempt of a student. To deal with the partial credit score, we came out with an approach of our own. We call it our weight approach. There are some work regarding partial credit score, but there was no work that we found that changed BKT in order for it to fit partial credit score. So the idea behind our partial credit score approach is that mastery learning is a weight summation of correct and incorrect portion of the response. So we took the equations of BKT, the probability of ln given evidence, that the evidence in the BKT is just a correct or incorrect, and we adapted it so it will be able to capture the knowledge in partial credit score. So it will be a weight summation of the correct version of the response and the incorrect version, and the score is the actual score that the student got for that question. We also adapt the empirical probabilities technique to fit the model parameters. The empirical probabilities is a heuristic approach to deal with, to fit model parameters. And we use that approach, we change the equations of that approach so it will be able to capture the partial credit score knowledge. To deal with students from different ages who solve the same questions, we came up with a new model, we call it grade model. And we actually introduced a grade node to that BKT topology, and we learned the probability of guess and the probability of slip for each grade of a student. And now that we had different models, we wanted to take all those models, to put them together, to test our weight approach, and to find out which model fits the data the best way, and to see if our weight approach is valid. So we evaluate our weight approach and our model against two domains, the K9 domain dataset of LNet that I introduced before, and the assessment data that was used by Ostro in our paper. And as I said, we wanted to evaluate the partial credit score approach and the different models. And here you can see some statistics about the data. With the K9 dataset, we had 4 different years of data, and with about almost 5 million records, so which is kind of a lot. And I'm going to present just the K9 dataset evaluation. So here you can see it. On the y-axis, you can see the RMSE value. Lower is better. And on the x-axis, you can see the different models. I'm going to introduce one of them separately. The simple model is the simple BKT model. The grade model is our model to deal with the grades of the student. The count model, the KT-IDM. A KT-IDM grade model is a model that you learn the probability of guess and the probability of slip for each grade of a student and for each question. The KT-IDM count is the same idea as the KT-IDM grade, and a model that combines them all, the KT-IDM, the count, and the grade. And the different colors represent different ways to deal with the partial credit score. We tested our weight approach against the basic threshold approach. In a threshold approach, everything above a certain value is considered as a correct response, and everything below a certain value is considered as an incorrect response. And we tested it against two thresholds, a threshold with a value of 1 and a threshold with a value of 0.75. And you can see that our weight approach with the color blue managed to outperform the two threshold approach in every other model. So we felt comfortable with our weight approach, and we tested it. We test also the different models, and you can see that once we introduce the KT-IDM model and its variation, it improves significantly the RMSE value. Out of all those models, the best model was the KT-IDM count. It achieved the lowest RMSE. But does it necessarily mean that we should always use the KT-IDM count model? Not necessarily. For some instances, we saw that other models, even more simple models, can achieve better results than the KT-IDM count. And it was also stated at the KT-IDM paper that the simple BKT can sometimes outperform the KT-IDM model. So we took that idea and we implemented it, and we used the model, and we come up with a model selection algorithm. The input for that algorithm is a set of possible BKT models and the response, and the output of that model is the best model that fits that response. And we tested it a bit differently. Since we wanted to deploy the system in the 2015 data, we used the 2015 data that we had as a test set, and we used as a train set the 2009, 11, and 14 data. And we again, the y-axis is the RMSE value, and the x-axis are the different model. We called our model selection the mixed model, and you can see that once we used our mixed model technique, it improves significantly the RMSE values against all those other models when we did it in that evaluation. So we had a model that we felt comfortable with, and we wanted to use that mastery learning model to sequence questions to students. There is a lot of work regarding sequencing, and I'm not going to discuss it all, but none of that work used mastery learning, used BKT at its core, and that is what we wanted to do. And here you can see the algorithm as it was shown in the paper. For a detailed explanation about the algorithm and all the implementation details and everything, you can look it up in the paper. And I'm just going to discuss about the intuition about that algorithm. So the intuition behind it is that first of all, we want to practice the student in the knowledge component or skill that he needs the most practice, and that skill is the skill with the lowest probability of being in a learned state. Then once we have that skill that we know that we want to practice him, we want to find a wanted score. The wanted score is a score that is going to be composed with the probability of being in a learned state for that student in that skill. And then we are going through all the questions in that skill and predict the score that the student will get for each questions. And then we compare the prediction against the wanted score. And we choose the question that minimize the difference between the wanted score and the prediction. The prediction is done by the BKT equation to predict the correct value. So that's the main intuition behind that algorithm. And we had a sequencing algorithm, and we want to use that in the classroom. So we deployed the system in 2 different schools in Israel. In the last 2 months of the school year of 2015, with grade 4 and grade 5 students. We did a pre-test to make sure that the student in the BKT, in the 2 groups are the same in terms of learning and knowledge. And we compared our BKT sequencing algorithm against a pedagogical expert algorithm that was called an ascending algorithm. The idea behind that algorithm is that the student will get a sequence of questions in an ascending level of difficulty. And each bin of level of difficulty, the questions were chosen randomly. That's the idea behind that algorithm. So I'm going to present you just one of the schools, the evaluation on one of the schools. So we had a group size of 26 students in each group. And the 2 main things that is interesting here is that we can see that the students who use our BKT sequence algorithm were more engaged with the system. It took them 74 seconds to solve a question compared to a student who used the ascending algorithm who took them 42 seconds to solve a question. We also saw that a student who used our BKT sequencing entered the system more frequently compared to the ascending algorithm. And we also tested it a bit differently. The student could use the system whenever they want. They could use it during school time or during home time. And we wanted to make sure that during home time, They also add more logins using our algorithm, and that's exactly what happened. Students who used our algorithm add more logins even during home time. Here you can see the level of difficulty, the bins of level of difficulty. There were 5 levels of difficulties, and our BKT sequence algorithm gave the students a more difficult question compared to the ascending algorithm. And when we look at the results, we can see here the graph with the result, the average score of the students compared to the level of difficulty. And students who used our BKT sequence algorithm managed to get better score in the 4 level of difficulty, which is almost the highest. The ascending algorithm managed to achieve better result in the first level of difficulty, the level 1 difficulty, and we assume that that is because students who solved level 1 difficulty with the ascending algorithm solved twice as many as the BKT sequence algorithm. That's one of the assumptions that we make. And we also wanted to ask the students if they feel that our sequence of questions help them to understand the topic better. So we asked them, how much do you feel the question help you to understand the relevant topic? And we gave them 3 options: did not help at all, helped a little, or helped a lot. And the BKT sequence scored an average of 2.2 out of those 3 options. And the ascending algorithm scored an average of 1.53. So students who used our BKT sequence felt that it helped them understand the topic better. So I want to summarize my work. We extend BKT so it will reason about e-learning challenges. We came up with an algorithm for model selection to choose the best performing BKT on data. And we provide an algorithm for sequencing a question to students that use the mastery learning model, and we evaluate it against 2 different schools. What we want to do next is to compare our BKT sequencing against a more complex approach. We also want to compare the algorithm against different manual strategies of sending algorithm. And lastly, we want to assess the advancement in learning using a pre and post test. We just use the pre-test. And that's it.
We have plenty of time for questions. And there are a few. Good.
Hi. Thanks for the presentation. Like you did the survey with the students to understand whether it helped or not, did the pedagogy experts look at the sequence and say whether that sequence made sense and it was actually better?
Sorry, can you repeat it?
So, like you did the survey with the students, did you also show the sequence to the, say, the content experts or the pedagogy experts to get some feedback on whether that sequence made sense from the pedagogy perspective?
Yeah, before we even entered the classroom, we asked pedagogical expert to look at the sequence of questions to see if it makes sense, and we did some iteration to improve it. The first time that we tried it, it didn't make sense, and then we improved it with and I'm discussing it a bit more in the paper with implementation details, so it will make more sense.
Okay. Just to build on that idea a little. Right, if you have a room of first graders, the probability, the L0 for that room of first graders of knowing calculus is 0, right? But it doesn't follow that we should recommend them calculus problems to solve, right? So there's some prerequisite structure, certainly, among these skills that you want to be able to represent somehow. And so what I wonder is whether you can conceive of a way to embed prerequisite structure in your adaptive sequencing.
I'm going to answer it a bit differently. The student who used that system, the skills that they could choose to solve are skills that were relevant to them as a 4th grader or 1st grader. So we knew that information, and we didn't recommend like from a general all the skills that there are. So the student could choose which topic that he wants to practice, and then we recommend out of those topics. Kind of answered your question?
Neil Efron from Worcester Polytechnic Institute. Really interesting, and I'm really glad you were able to use our publicly available data. It always makes us happy if we can share data sets. Can I ask a question? How did you said there was a mixed model that XU compared to these other ones.
Mm-hmm.
What were you doing there? Did you actually do like random forest to make this, or did you just average the models, or did you do like a decision tree to pick which model is best at which time?
Okay, so what we actually did with the mixed model is that we did k-fold cross-validation on all the models, and then when we got the instance, we know what is the RMSE for that instance in each of the other models, so we know which model to pick in that situation.
So then you pick one of them, the best.
Yeah.
You're not like average. Okay, nice.
Zach Paros, UC Berkeley. Really great to see some of these methodologies actually applied in real life and see that they can have an effect on the student. So thank you for doing that. So the question is the sort of pedagogical theory for why this item sequencing was beneficial. So you could look into different item orderings with the hypothesis that maybe you want cover story first and then the abstract version of the item, right? So you could find these kinds of ordering effects, or it could just be sort of a zone of proximal development thing, right? Mm-hmm. Where you just want to give the student the item that's at the appropriate difficulty level for them at the time. So what do you think, or the subject matter experts that you interviewed, what do they think was sort of the pedagogically beneficial value for the suggestions versus the standard practice?
I can tell you what they were the most afraid of. They were really afraid that the student will get like a difficult question that he can't solve. That was their most, they were feared of that the most. We think that we should give the student questions that fits his learning it in that moment, but a bit easier question than, like we tried that on the first iteration that we did with the content expert, and it didn't work because it was too difficult for the student. So that's the idea. We believe that we should give it. That's what we tried.
So the default was maybe too aggressive.
Yeah.
For the increase in difficulty.
Yeah, the increase of knowledge was too high after you solve a difficult question, for example, and the student is not ready to face a more difficult question. So we try to make it more incremental.
Any other questions? Thank you very much.
Thank you.
Can we do a switch?